Dissecting the Proton Structure in Threads and Spinons Theory. In this theory, the proton is a dynamic entity composed of threads and spinons, rather than traditional particles like quarks and gluons. It is structured as a layered system with distinct properties and interactions. This explanation dissects the proton from its outermost region to its core, offering a complete understanding of its nature. 1. The outer shell. Thread cloud composition. The outermost region of the proton consists of a dense cloud of threads that extend outward. Function. Threads create the structural boundary of the proton. They radiate outward, interacting with threads from other particles to generate the strong nuclear force. The tension within these threads contributes to the proton's stability and energy field. Observable effects. This outer shell defines the proton's size and mediates its interaction with other particles, such as neutrons in the nucleus. 2. The intermediate zone, thread-spinon matrix composition. This layer is a dynamic interface where threads interact directly with spinons. Spinons are tiny rotational entities embedded within the threads. Function. Spinons contribute to the proton's positive charge through synchronized rotation. The threads in this region support the alignment of spinons, amplifying their energy and charge effects. The interaction of threads and spinons creates a dynamic lattice that distributes energy across the proton. Observable effects. This zone influences the proton's magnetic moment and contributes to its intrinsic spin. 3. The inner core, spinon cluster composition. At the core of the proton is a dense cluster of spinons, aligned in tightly bound stacks. Function. Spinons in the core rotate collectively, generating the proton's intrinsic spin and mass. The core serves as the source of threads that extend outward, providing energy and structural integrity to the outer layers. Observable effects. The core governs the proton's high-energy interactions and stability. Its spinon stacks contribute to the proton's quantized energy levels, derived structures within the proton thread loops. Nature. Localized loops of threads formed by the internal tension. Role. These loops stabilize the proton's structure and manage energy flow. Spinon stacks. Nature. Groups of spinons rotating in synchronization within the proton's core. Role. These stacks define the proton's energy states and magnetic properties. Resonance nodes. Nature. Points within the intermediate zone where thread tension peaks. Role. These nodes amplify spinon rotation and distribute energy effectively across the proton. Formation of the proton. The Threads and Spinons theory proposes that protons form through a gradual, dynamic process involving threads and spinons. Thread compression. Threads, under external forces such as vacuum pressure, compress into a dense configuration, forming the initial framework of the proton. Spinon emergence. Spinons appear as threads under tension begin to rotate. These spinons synchronize, creating a dynamic rotational field. Dynamic stabilization. The interaction between spinons and threads stabilizes the proton, ensuring its long-term structural integrity. Charge and mass generation. The proton's positive charge arises from the synchronized rotation of spinons in the intermediate zone. Its mass is a result of the tension in the threads, amplified by spinon interactions. Redefining components of the proton. Traditional particle physics explains the proton as being composed of quarks held together by gluons. In the Threads and Spinons theory, quarks reimagined. Quarks are replaced by localized thread loops and spinon clusters, which form the proton's internal dynamics. Gluons reimagined. Gluons, which mediate the strong force, are replaced by thread tension waves, which propagate between protons and neutrons. The strong nuclear force. The strong nuclear force is redefined as the tension-mediated interaction of threads extending between particles, rather than the exchange of gluons. Observable phenomena explained. Proton mass. The mass of the proton is a result of the collective tension of threads and the rotational energy of spinons. These components act together to generate the observed mass. Proton spin. The intrinsic spin is produced by the synchronized rotation of spinons in the proton's core and intermediate zone. Positive charge. The proton's charge is explained as a field generated by the directional rotation of spinons and their interaction with the threads. Magnetic moment. The magnetic moment arises from the collective rotational dynamics of spinons and the alignment of threads in the intermediate zone. Experimental validation and predictions. The Threads and Spinons theory suggests new ways to validate its claims. Spinon isolation. High-energy particle collisions could theoretically isolate individual spinons or spinon stacks for study. Thread tension measurement. Experiments could measure the effects of thread tension through precise observations of nucleon interactions or by studying tension waves. Resonance detection. The resonance nodes within the proton could produce unique signatures in particle scattering experiments. Strong force testing. The theory predicts specific thread tension behaviors in the strong nuclear force, which could be tested in high-energy nuclear physics experiments. Why this theory matters. Unifying forces. The theory offers a unified explanation of the proton's structure, charge, spin, and mass using threads and spinons. Simplifying subatomic physics, it reduces reliance on hypothetical particles like gluons and provides a more tangible, testable framework for understanding the proton. New experimental pathways. By focusing on thread tension and spinon dynamics, the theory opens the door to novel experiments that could challenge or validate its predictions.